All right. Now that we understand what capacitance is and the sort of factors that are affecting the capacitance of a system, we're now going to put these capacitor objects in circuits. So before we start including resistors and all our other circuit elements, we're just going to be connecting capacitors to each other to start. So a capacitor in a circuit diagram is two parallel lines representing two parallel plates, not to be confused with the battery, which is two parallel lines of different length. So the first problem we're going to consider is what happens when we charge two capacitors and then connect them. So if we connect two charged capacitors, we are claiming that we get the following results, which will allow us to solve for all the charges. First, the potential difference across each capacitor must be the same. So we're saying the delta V's must match. That's one equation we can write. And then we can also say the charge of the system must be constant. So we actually see both of these rules, and this looks like a problem we've done before. Potentials are the same, Q is constant. Well, that's actually just this problem, where if we remember from electrostatics, we had like a big sphere, and we had a little sphere, and they held different Qs, and we were interested in finding the amount of charge that ended up on each of these conducting spheres. So realize it's the same idea, right? Because if I close this switch and allow them to reach equilibrium, well, it's a conductor in equilibrium because these conductors, these capacitor plates are metal. So we know that eventually, of course, charges are going to move around and they're not going to be equal originally, but eventually some sort of equilibrium will be established where we have everything on the top end of the circuit is at some potential, and then everything on the bottom of the circuit is also at a different potential. But notice, these capacitors are both going to share the same potential difference, delta V, because they both go from red to blue. So we can use our same technique as last time. And also we know this charge can't just magically vanish. If that's the amount of charge I have to deal with on each plate, it somehow must work out to that number. It can't just vanish. So we'll see a lot of similar trends to last time when we did the two-sphere problem. You could also argue that you could say, okay, I don't really want to use the conductors are equipotential surfaces argument. And instead, you could say, well, this is a circuit. And this is actually capacitors in parallel. Why is it parallel? I know it definitely looks series, because I can connect the capacitors to each other, nothing else. But the definition of parallel, this is really important, is that you form a closed loop with the other circuit element and nothing else. So this is actually parallel, not series. So if you have two capacitors connected to each other, it is parallel. You actually cannot connect two capacitors to each other in series with nothing else. Now, if you have a battery or if you have more circuit stuff, of course you can get capacitors in series. But two capacitors by themselves is only parallel. And we know that from Ohm's law and Kirchhoff's loop rule that voltage drop has to be the same in parallel. Because I can travel this way to that point, or I could go all the way around here to that point, and the potential differences must match. So loop rule guarantees potential difference is the same in parallel. And the one change here from last time is we have this idea of capacitance. And capacitance and voltage drop are certainly related, because if Q is CV, V is Q over C. So we can relate the voltage to the charge, and that gets us a linear system with Q's. So we can write our equations, and we have our two equations, two unknowns, and then we can solve. So we'll begin with sort of the base case example here. In the circuit shown below, the switch is closed, and we allow the network to reach equilibrium. Assume the top plate of each capacitor is positively charged. So we always assume a capacitor holds equal and opposite charges. So we have plus 10 microcoulombs on this plate, minus 10 microcoulombs on the other. We have positive 8 microcoulombs on this top plate, negative 8 on the other. It does actually matter. There's a homework problem, I think, where we see that it does matter. which way these plates are connected to each other. So first, let's calculate the initial voltage or potential difference across each capacitor before we close the switch. So we have two capacitors. We have the 2 microfarad, and then we have the 4 microfarad. And because we know that Q is equal to C delta V, we know delta V across a capacitor is Q over C. So delta V is Q over C. And you actually don't need to convert using scientific notation if all of your units match. So we can get regular volts if we have microcoulombs and microfarads because the 10 to the minus 6 will divide out. So Q over C, Q we said was 10 microcoulombs, and C was 2 microfarads. So that gives 5 volts. Notice it's not 5 microvolts, it's 5 volts. Because the top one is 10 times 10 to the minus 6. The bottom one is 2 times 10 to the minus 6, so 10 to the minus 6 cancels out. And now we see a similar idea. Delta V is Q over C for the 4 microfarad. And I do believe this is 8, because that would make my numbers work out nicely. So we get 2 volts initially across this. So this actually proves, that this is not in equilibrium, and that something is going to happen when we close the switch. Because we have, essentially, there's 5 volts across the 2 microfarad, and there's 2 volts across the 4. So this essentially means we got a big battery trying to push this way, because that's a big potential difference. And then we got a small battery trying to push this way. So if we compare these voltages, so we know this is 5 and this is 3, we see that we are going to get a net current this way, right? Because the 10 microcoulombs is too much. That's too much charge on this positive plate. The voltage is higher across capacitor 2. So that means that it needs to release some of its charge. And since we go from high potential to low potential, that gets us that. So which way does it go? So current flows clockwise. And this is from, so current flows clockwise. Oh, let's also make sure this makes sense. So also, if we looked at it the other way, we would say that this capacitor plate has too much charge. It has too much positive charge because its potential difference is higher. This means I have to give some of the positive charge to the other plate. So that's fine. We definitely get clockwise up there. Well, does it work for the minus charges too? Well, let's see. We could also say, for the same reason, this capacitor plate has too much negative charge on its bottom plate. So the negatives have to go this way. But wait, doesn't that seem like an issue? Because we just said the current is clockwise. This definitely isn't clockwise. Well, now we have to remember it's conventional current. So yes, the electrons would be going to the right on the bottom, but the conventional current is still going to be clockwise because conventional current is which way are positives moving. So if negatives are moving right, positives would move left. So no issue, actually. So current flows clockwise, and that's because current flows. Yeah, we'll say flows. I know people don't like saying current flows, but current flows from high potential to low potential. I will continue to say that current flows. What we should say is the charge carriers, positive charge carriers, are moving clockwise, but whatever. Calculate the charges on each capacitor once equilibrium is reached. So this is where we write our 2x2 system. So we don't know the Q's. So our first equation It's going to tell us that delta V across the 2 microfarad capacitor is equal to delta V across the 4 microfarad capacitor. So I know that Q across the 2 microfarad divided by C of the 2 microfarad is equal to Q on the 4 microfarad divided by the capacitance of the 4. Because we said that V is Q over C. And now we can do a bit of simplifying, right? Because we know what these C's actually are. We said that C2 are 2 microfarads. This is 2 microfarad is equal to Q4 divided by 4 microfarad. And notice we have a nice linear multiple going on here. We see that if I multiplied both sides by this 4 microfarads, we would see that Q on the 4 microfarad capacitor is exactly twice the Q on the 2 microfarad. That should make sense, because remember that capacitance tells you how much charge it takes to get a certain potential drop. So if I have a bigger capacitance, I need more charge to get the same voltage drop. And then we use our charge conservation equation, which says Q on the 2 microfarad plus Q on the 4 microfarad has to be some constant. And we actually know what that constant is, because we have 10 microcoulombs and 8 microcoulombs as our 2 plate charges. So Q total is 18 microfarads. So we can now, or microcoulombs, sorry. So we said Q2 is Q2. Q4 is twice of Q2. And our total charge of the system is 10 plus 8, which is 18 microcoulombs. So we get 3 times Q2 is equal to 18 microcoulombs. So this means Q2 is equal to 6 microcoulombs. So that's the charge on the 2 microfarad. And then, using either equation, we actually said that Q across the 4, charge on the 4 is actually double that. So we can see that Q on the 4 microfarad is exactly double that, which is 12 microcoulombs. As a quick sanity check, we see both equations are satisfied because we got double across the bigger capacitance, and we see that 6 plus 12 is definitely 18. And again, we got that 18 by adding the plate charges of the plates that were connected. So that's why I say it actually matters which way the orientation is of this. Because if I connected the positive plate to the negative plate, the charges would cancel partially. So we'd get a lesser total charge to deal with. All right, let's verify it's in equilibrium by calculating all the voltages. So we're going to do the same thing. And of course, you know how I operate at this point. We will always do a copy paste when possible. So we see that it wasn't in equilibrium before. So 10 and 8 definitely weren't the answers. What did we say the answers were? We said it was 6 and 12. So V is Q over C. 6 divided by 2, that's definitely 3. 12 over 4, that's also definitely 3. So it works, right? Because we said 2 conductors are in equilibrium if the potential difference across them is the same. Or if they're at the same potential, same idea. Because if they're both at the same potential, there's going to be no charge flow. Charge isn't going to flow anyway because it's going to flow downhill. And if they're both at the same elevation, of course, you get no charge flow. Calculate the total energy stored by the network after equilibrium is reached. So you can use any energy formula you'd like. I actually think it's easier to use, we'll show all 3 just because we can. U stored in a capacitor, by definition, is half of Q delta V. And we went through this argument last time that it's a half of QV because it doesn't actually cost any energy to separate the first bundle of charge. But as you're separating more and more charges, it starts to build up. So it's actually half of what it would cost to move all the charge at that voltage. Then we do some substituting. We can write this as 1/2 C delta V squared or 1/2 Q squared over C. I am going to pick 1/2 CV squared because V is the same. And it's less work for me there. All right, so total energy stored by the network. So I know that my U total is going to be 1/2 times C delta V squared for the first capacitor, plus 1/2 C delta V squared for the second capacitor. So what is that? We get 1/2 times C2. C2 is 2 microfarads. And our voltage was 3 volts. I'm actually writing the units out because we can see what is going to stay constant throughout our unit process and what's not. So if we do this, we actually get units of microjoules. I like that better because it avoids having to use scientific notation. So let's see, we get 1/2 of 2. That's obviously 1. So we get 9 microjoules stored in the field in the first capacitor, and then double that, 18 microjoules. So we get 27 microjoules of energy stored. But if we didn't like that and we actually want it as scientific notation, this would be 2.7 times 10 to the minus 5 joules, for those who want to do it that way. So again, if you do stuff in units of micro, if you keep it in microcoulombs and micro farads, it'll work. And actually, if you calculate this energy stored, this is actually a lower energy than it started with if you plugged in the beginning charges and voltages into this, which is interesting. There's a couple arguments as to why. You can think of it as the charges move, they have to get sloshed around in the wire, sort of like water in a tube. All right, now we'll do this one quicker. This is a symbol version. Yeah, this is the same question. It's just a symbol version. So we're connecting the positive plate of one capacitor to the negative plate of the other. What's the equilibrium charge on each plate? So let us begin. So same idea as before. We know that at equilibrium, they have reached the same potential difference across the plates. So we know that Q1 over C is equal to Q2 over 2C. Because again, we have a different capacitance over here. So multiplying through, we get that same ratio as last time where we see that Q2 is twice Q1. So that's definitely expected. That's definitely expected because twice the capacitance, it should hold twice the charge to get the same potential difference. Then, same idea here. We know that Q1 plus Q2 is always a constant. And more specifically, we said that Q2 is 2Q1. And what is the constant in this case? Well, we see that I have 11Q across on one plate, and that plate gets connected to the plate holding negative 2Q. So my net is not 13, it's 9. It's actually 9Q. Because again, these charges are going to neutralize slightly. This charge has two signs. It's positive or negative. We're actually connecting positive to negative. So the 11 and 2 shouldn't add, they should subtract. Now, if I made this a plus 2Q and connected the positive plates, then you would get 13. So we get 3 times Q1 is equal to 9Q. So Q1 is equal to 3Q, and Q2 is exactly double that, which is 6Q. So again, all I did is once I found this was 3Q, I knew that Q2 was exactly double that. And we can check it works because 3 plus 6 is 9, which is that. Oh, I got purple and 9. J.J. McCarthy reference. Equilibrium voltage across each capacitor. Well, let's check. So we know they should match, right? They should match. Shouldn't matter which one we do. So if I check C1, we know delta V is Q over C. And we said Q1 was 3Q. So we get 3 times the quantity Q over C. And then we can also check our second capacitor. Same idea, Q over C. And of course it's going to work out, because yes, we definitely have double the charge across on Q2, but we also have double the capacitance. So we see that we do get 6 divided by 2, which is 3, which is our expected result of 3 Q over C's. All right, now we have a bit of a ranking to do here. The 3 initially unconnected capacitors have capacitances C, 2C, and 3C in order. So this is C, this is 2C, and this is 3C. A switch is then closed to connect the 3 capacitors, and then the network reaches equilibrium. Rank the energy stored from least to greatest after reaching equilibrium. So only this capacitor is charged, not that it actually matters. So as soon as we close the switch, we know that a bunch of charge is going to get pumped from the top of C1, and some of it is going to go here, some of it's going to go here, and we're really interested in, once equilibrium is reached, how do the energies compare? So of course, we probably can't just come up with the ranking instantly. We want to start with thinking about our justification. And it says qualitatively. So what does qualitatively mean? It means don't derive an expression. So we can pick our favorite capacitor energy formula. I would say that it counts. Now, if we wanted to be really, really qualitative, we would say don't reference the manipulated capacitor energy formulas, but these are well known enough that I don't really count it as manipulating. So which one do we want to use? Well, we're comparing. So if you're comparing, you want to compare using things that are the same. So if you can find something that's the same, you can compare the differences more easily. So what's the same at equilibrium? Well, once they've reached equilibrium, potential here is equal to the potential everywhere on top, and the potential on the bottom is equal to the potential everywhere on the bottom. So we see that it's the same potential difference. So we know it's the same delta V. And why is that helpful? Well, we absolutely have a capacitance formula involving delta V. So notice we know nothing about Q. So I would like to avoid Q. And we absolutely can, right? Because we have a formula that says U across a capacitor is equal to 1/2 C delta V squared. So if U is 1/2 CV squared, and the V is the same, right? This is the same. That means that we're just ranking the capacitance. So we see that as C goes up, delta V goes up. Now, I will come back with like a more qualitative justification. This at least gets us the answer, because we know delta V is, oh, not delta V. Not delta V. I'm looking at U. We know what I meant. I'm sure that we knew what I meant. U goes up. So we're just ranking the capacitance. So C1 has the lowest capacitance, so it stores the least energy, then C2, then C3. So how can we justify this qualitatively? Well, I'm totally fine with the explanation on the left, by the way. I better be. I came up with it. But this is what you could say if you're really trying to avoid manipulating. Now, this is the fundamental fact, is that U is proportional to Q delta V. Because that's just the definition of potential energy. And I said proportional because maybe you don't know there's a half there. So we said that delta V is the same at equilibrium. So if delta V is the same in equilibrium, we also know that as C increases, more charge is needed for same delta V. I know it got cut off a bit there. As C increases, more charge is needed for the same delta V. So that means larger C stores more charge at the same delta V, so U increases. So let's kind of argue through that real quick. U is proportional to Q delta V, and delta V is the same at equilibrium. So we see that as C increases, you need more Q for the same delta V. That's what capacitance means. The more capacitance, the more charge you need for the same voltage. So if you are at a larger capacitance, you're storing more charge at the same voltage. So U goes up for the larger capacitances. So that is the more like, that is like the truly qualitative way. This is totally legit, by the way. Just, it's easy just to argue that. What we wanted to not do is like pretend the equilibrium charge, or pretend the total charge of the network is Q, figure out how it distributes, plug in, do a ratio. We don't want that. What is that going to be? I believe the charge splits into sixths. Yeah, if you actually are curious, if this charge was Q, someone can verify this, but I'm pretty sure this will be right. This would be Q over 2. This would be Q over 3. And this would be Q over 6. Is actually the charges, I believe. If we're saying capital Q is the total network charge. Oh yeah, we can see that works, right? Because Q over C is 1/6 Q over C. Then we get 1/6 Q over C, 1/6 Q over C. So it actually does work, but that's not what we wanted to do. All right. So we've moved around it for long enough. Now it's time to put these in real circuits. So when a network of capacitors are connected to batteries, we have the following properties. Two capacitors in series have the same Q on adjacent plates. And that's because of conservation of charge, and it's our analog to the junction rule. Two capacitors in parallel must have the same potential difference. We've already talked about that one. And if we use these conditions, we can actually derive expressions for equivalent capacitance. We can get a series and parallel. And this is actually not a typo, right? This is actually the opposite of resistors. This is not a typo. So maybe let's write some things here. This is the same Q. And this is the same delta V. So what is equivalent capacitance? So remember we defined Req as, well, delta V total is the battery. We said the total EMF divided by the total current. So capacitance, since capacitance is Q over C, it's the total Q. Or since capacitance is Q over delta V, it's the total charge divided by the battery voltage. So this is what series looks like. This is what parallel looks like. Same thing as resistors. So the reason we didn't have series capacitors is when they were connected to each other. So if there's no battery here, that's actually series. Or sorry, that's actually parallel. Because they're connected to each other and nothing else. But this series totally works because that battery's there. So maybe just as a reminder, this is the same Q. This is the same delta V. And the reciprocal formula always outputs a lower result. So this is a lower capacitance. And the parallel result is adding capacitances. So that's obviously a higher capacitance. So like, remember when we combined resistors, we said resistors in series were always greater. The Req was always greater than the individuals. And in parallel, the Req is always less. Of course, we get the opposite thing here because we have the opposite formulas. All right, let's show it now. Let's verify our series and parallel rules. So this uses Kirchhoff's rules. So we have to remember what those are. So remember that we can model our potential as color. Like this, right? Because we're going to drop some of the battery voltage across C1 and the rest of it across C2. So we know that capacitance, equivalent capacitance, is defined as the total Q divided by the total delta V. So let's figure out which one of these we can actually substitute for. And maybe instead of epsilon, we might want to call this delta V total. Same idea. So how can we do that? Well, we said capacitance or charge is the same in series. So if we can write everything with a Q in it, the Q divides out. We're going to say the Q on C1 is the same as the Q on C2, which is Q. And then what is the total voltage drop? Well, I'm dropping some volts here, and I'm dropping some volts here. So we actually have two voltage drops that are contributing to our total. So we can write this as the delta V across C1 plus the delta V across C2. And we do know what that is, because delta V is Q over C. So we get Q divided by Q over C1 for voltage drop across C1. And then we got Q over C2 for our voltage drop across C2. And notice this looks exactly like the resistor proof, where magically the Q all factors out because everything is proportional. So we get CEQ is equal to 1 over C1 plus 1 over C2. But again, I find that very clunky to look at. This is correct, but I find it very clunky to look at. So again, remember that a negative exponent means division. So I can just say this is 1 over C1 plus 1 over C2 to the negative 1. And we got to scoot this over so we can see it. All right. So that's series. What about parallel? Well, given that the parallel formula is a lot simpler, we can guess it probably takes one or two less lines. So remember, in parallel, you don't have the same Q, because different capacitances are going to pull more Q or less Q from the battery to establish the same potential difference, right? It's going from red to blue. So this one had the same Q. This system has the same delta V. So once again, our equivalent capacitance is just going to be equal to the total charge of the system divided by the total voltage drop. And the voltage drop is the thing that's the same in this system. Because the voltage drop isn't just this delta V and this delta V. We actually know what it is. It's the EMF, epsilon. So I know my delta V total is actually epsilon. So what is Q total? Well, we know that some of the Q is getting put on C1, and some of the Q is getting put on Q2. So again, that's like, this is not like we had in the previous case where they share the same Q in a series, because it's like a junction idea, where some of the charge splits to go here, some of the charge splits to go here. And then what is delta V total? Well, delta V total is just going to be our battery EMF epsilon. So now we got to get some capacitance relationships in here. So just like we said delta V is Q over C, we can also say Q is C delta V. So we can plug in C delta V for each of these Qs. So CEQ is equal to C1 times epsilon for the first capacitor, C2 times epsilon for the second capacitor, and then we see that everything divides out. So we get the equivalent capacitance is just C1 plus C2. So we see we get our two cases here. So again, the whole trick to deriving these expressions is picking the thing that is constant so it divides out. So our charge was constant in series, so we wrote everything in terms of Q. Our delta V, potential difference, was constant in the parallel case, so we wrote everything in terms of the battery voltage epsilon. So that's our little trick to deriving it. Again, it's important to see where these come from. So here, the delta V was the same. The delta V was the same, so they shared charge between the two that split. Here, the charge was the same, so they shared how the delta V was split. So they either split the Q or split the delta V. All right. We just got a big network of capacitors here. And we want to find the equivalent capacitance between points A and B. So essentially, how can we crunch all these down into a single capacitor? So again, the rule for this is just combine things that are directly in series or directly in parallel first. All right, what are you? Well, you two are certainly in series. Now, if this was resistors, it would definitely be 18, but it's not, right? Capacitors behave opposite of resistors. So this is 1 over 12 plus 1 over 6 to the minus 1. And that is something. Let's see. I'm going to guess. I know 3 and 6 makes 2. So this is going to be 4. And then these capacitors are in parallel. So that's just addition. So this is 6C. Alrighty. So now we can condense our network a bit. So our top branch is 4C. Our middle branch is 1C. And our bottom branch is 2 6s. Right? Because I didn't get rid of this other 6. So now we can just combine the 2 6s. So if we did this like the official way, we'd do this as 1 over 6 plus 1 over 6 to the minus 1. Or if you remember our trick, we said 2 resistors in parallel that were identical. The number of resistors you have, you just divide by that number, right? Because if capacitance behaves like this in series, it's going to just halve. So this is actually 3C. So now we can just draw ourselves one final circuit, because we have you are 4, you are 1, and you are 3. So our equivalent capacitance is just going to be the sum of these. So CEQ is just going to be 4C plus 1C plus 3C, which is 8. So a nice little exercise there. It worked out to a nice number. So yeah, people usually don't mess this up. Just remember it's the opposite rule. And it is on the formula sheet, so you shouldn't mess it up. So series capacitance is the reciprocal rule. Parallel is the addition. Also, we could have argued that because capacitance, just as a side note, is epsilon naught A over D. So parallel, you're increasing area. So C should go up. But in series, you're increasing D, the plate separation. So C should go down. All right, what is the total energy stored in this capacitor network? Well, I certainly know a bad way of doing it. A bad way of doing it would be, what is the energy on this capacitor? What is the energy on this capacitor? What is the energy in this? What is the energy in this? And by energy in the capacitor, I mean energy stored in the electric field in the capacitor. Sorry if I misspeak. But we're not doing that. That's obviously not the right, I mean, it works. But we just talked about equivalent capacitance. So there must be a better way. And of course there is. What is that? Well, we know that the idea of equivalent capacitance means we can replace the entire circuit with one capacitor that incorporates all of the information. So we can say that U total is equal to 1/2 Q total delta V total, which is equal to 1/2 CEQ delta V total squared, or it's equal to 1/2 Q total over CEQ squared, for my Q. Okay, well, notice I know absolutely nothing about Q. So I definitely want this middle energy formula, which is really the star of our show today. This is the one we've been using a lot. So we're going to be interested in that because we know that our total energy stored by the network is going to be 1/2 times CEQ times, what is delta V total? Well, delta V total is how much voltage drop is across all the capacitors combined. Well, I'm connected to a battery, so it is just battery voltage. All right, what's CEQ? Let's figure it out. This is not difficult. These are 3 capacitors in parallel. So parallel capacitors add, so we get 1, 2, and 3, which makes 6. So what does that leave us with? Well, that leaves us with a 3 and 6. That leaves us with a 3 and 6 in series. So then we just add, we just do the reciprocal rule. So CEQ is just 1 over 3 plus 1 over 6 to the minus 1 times C, and that is 2. Also, another shortcut if you didn't know. If you're doing the reciprocal sum idea with 2 objects, the numerator is always the product of the 2, and the denominator is the sum. So I actually found this by taking the product of 6 and 3, which is 18, and divided by the sum of 6 and 3, which was 9. So that's actually how I'm able to do these in my head. And it helps when I write them to work out. So what does that mean? Well, that means that U total, which we said was 1/2, times the equivalent capacitance times the voltage squared of the battery. So the 1/2 and the 2 go cancel each other. So we just get C times epsilon squared. And now here is our daily reminder of, I call this the people who dislike themselves and want to do a bunch of algebra. So if you're one of those people, calculate everything about this circuit and add up all the energies and show that you still get C times epsilon squared. Good luck. It's not actually hard, it's just annoying. All right, now we'll do a numeric example. So this is very similar to our resistor problems we did that look like this, where this is a solve for everything problem, where we got a big table of all the voltage drops, stored charge, and energy. So let's begin just by doing the potential. So again, we said the potential is highest at the positive terminal of the battery, and we define that to be the battery voltage, stepping that up, because we always define the location of 0 potential in a circuit to be that negative terminal of the battery. So if I define 0 volts to be the bottom terminal, my potential at the top is going to be 20 volts because it gets stepped up. And notice I'm actually out of, I can't color this with just 2 colors because I need some sort of intermediate potential value for this. Because this isn't a series circuit, this isn't a parallel circuit, it's a combination. So let's do it. So now that we know this, it would be really nice if we knew the delta V across this capacitor. If we knew this delta V, it would be very nice. Because if we knew this delta V, we could unlock these voltage drops using the loop rule. Because we know that voltage drop is the same in parallel, and it has to work out to the battery. So if it was 18 volts across the first capacitor, it would be 2 volts across the others to get back to the battery. So that means that we need to know something. So remember that with capacitors, charge is the same in series. So if these were resistors, we would solve for the total current because the total current hits this resistor and we'd get a voltage drop and do it that way. We're actually going to do the same thing, just with charge. So we have some space here to work out equivalent capacitance. So first of all, this is easy, right? This is 10 and 2, which makes 12. Because capacitance just adds in parallel. And then I have a series. So my CEQ is just going to be 1 over 4 plus 1 over 12 to the negative 1. Because we see that we have the 4 exactly in a series with the 12. And avoid typing that in. I'm going to use product over sum just to do this in my head. So the product of 12 and 4 is 48, divided by the sum, which is 16. So 48 over 16 makes 3. To the best of my knowledge. If you're seeing this, it means I did it right. If not, I refilmed. All right, so what does that mean? Well, this unlocked one thing in our table. Equivalent capacitance was 3 microfarads. Battery voltage was given to us in the problem as 20 volts. So now we just use our capacitance relationships. Because charge is given by Q equals CV. So what is that? Well, I have 3 microfarads and 20 volts, so that's going to be 60 microcoulombs. And then for my energy stored, you can really use any of the 3 formulas. Let's use a different one. I'm going to use 1/2 Q delta V, so I can at least attempt to do this in my head. U is Q, sorry, it's U. I can at least try to do it in my head. So half of Q, so that's going to be 30, and then 30 times 20, that's going to be 600 microjoules. You don't have to use micro if you want. You can totally just write this with scientific notation. All right, so why does that help? Well, the thing that helps us is this, because we know that the total charge stored in the network is 60 microcoulombs. And that also means that the 60 microcoulombs is all going to this capacitor. So it definitely splits off like the junction rule with current later on, but all 60 microcoulombs can be found there. And of course, we could say this is found by Q equals CV, but we actually don't know that. We'll need it later, though. So what is the voltage drop? Well, voltage drop is Q over C, doing more manipulating. So I have Q, which is 60 micro, and C is 4 micro. So I get 60 divided by 4, which is 15 volts. We'll do energy last. So why is this helpful? Well, now we've done it. We've done what we wanted. We wanted to unlock this voltage drop. Because if that's 15 volts, that means that I started at 20 volts and I lost 15 or I dropped 15. So this is going to be 5 volts is my yellow color. And then if I went from 5 volts down to 0, that's of course going to be 5 volts across either of these capacitors. Because we're, again, Kirchhoff's loop rule says all of your voltages have to add up to the battery if you make a closed loop. And we see that that works, right? Because if I drop 15 across the first capacitor, it must be 5 across either of the others. So that tells us, using loop rule, that these are 5 volts. And now we can Q equals CV that to get our Q. So CV, 10 and 5 makes 50. CV, 2 and 5 makes 10. Oh, look at that. We got 50 and 10. We got 50 and 10, which certainly adds up to 60. And notice 10 is 5 times of 2. So this capacitor has 5 times the capacitance, so it required 5 times the charge. You could actually do some ratio shenanigans to do this in your head. All right, what is the energy stored? Oh man, we're really testing me here. I still like U equals 1/2 Q delta V, I think. Oh man. Okay, let's do it. The bottom one is the lowest, so I'm the least scared of this. 1/2 Q delta V. So that's 1/2 of 10, which is 5 times 5. This is 25. All right. This is just 5 times that, so that's 125. And then 1/2 Q delta V for this one is just 6 times that. Or no, it's not. It has a different voltage too. Let's work this out. Gotta think. We gotta lock in with our mental math. All right, 1/2 Q delta V. 1/2 Q is 30. 30 times 15. 30 times 15 is 450. All right. And it's going to work. How do I know it's going to work? Well, I just did it. That's why I paused for a second. I did a little verification in my head. What's the total? The total energy. If we add up our total energies, we get 450 plus 150, which is 600. That's what we expected. We said the total energy stored in the network was 600. And if I summed up all the individual energies, I did get that. So it matched. Very cool. So that's why I said for the people who hate themselves, they could totally find the total energy stored in this network by doing this approach. And it does actually work out. All right. So now we're going to do sort of an extension of these parallel capacitors where they're not really in circuits, but we can actually get clever by making these sort of dielectric sandwiches. So this is the first of the three we'll do. We say this parallel plate capacitor has total area A and plate separation D. We have three dielectric slabs that cut this into thirds. So we have a kappa, a 2 kappa, and a 3 kappa. So this is a third of the area, this is a third of the area, and this is a third of the area. So they're equally sharing the plate area. Let's figure out what the capacitance is. So because this is in the parallel and series capacitor section, we can actually model this as one of those two. And if we think about it, if you imagine like doing a little snip right there along the border, we see that this is definitely a parallel capacitor system. Because I can get from the top plate to the bottom plate by going through this capacitor, or this capacitor. I have three different routes, which is indicative of parallel. So this means that I can really just model the system as this. And let's do it like that. So I can model the system as this. I can model it as a kappa, a 2 kappa, and a 3 kappa, all in parallel with one another, as so. And it's really important here that we remember that the area was shared between the three. So you had a third of the plate area, you had a third of the plate area, and you had a third of the plate area. But they all have the same plate separation, D, because they all spanned the entirety of the gap. So now we just do parallel capacitance, because we said the capacitance in general is kappa epsilon naught A over D. That's our expression for just the capacitance of two plates. So for our system, we're finding the equivalent capacitance, which is 1 kappa times A over 3 epsilon naught over D. Then I have 2 kappa for a third of the plate area. And then I have 3 kappa for a third of the plate area. And we'll actually notice something when we do this answer. All right, let's work it out. So this is 1/3 kappa epsilon naught A over D. This is 2/3 kappa epsilon naught A over D. And you are 3/3 kappa epsilon naught A over D. So we get 1 plus 2 plus 3, which is 6 on top divided by 3, and we get exactly 2 kappa epsilon naught A over D. And we can do some sanity check to make sure this answer makes sense. So first of all, notice that the capacitance isn't going to be 1 kappa epsilon naught A over D, because that would be if it was entirely filled with the weak capacitor, or the weak dielectric. It's not going to be 3 kappa epsilon naught A over D, because that would be if the entirety is filled with the strong dielectric. And because we distributed these equally amongst the plate areas, we actually just got the kappa, effective kappa value was the average of the three. And the average of 1, 2, and 3 is, of course, 2. So we could have done this, actually, with some clever reasoning. And one more note about this problem is this is really strange, because the electric field here has to be constant. Because we have to get the same voltage drop. But we said the dielectric weakens fields in a capacitor. So how does that work? Well, just to spoil it, charge density isn't uniform on the plate. So you might get 1 of the charge, you might get 2, and you might get 3. So we actually do get a uniform. We get a uniform field that way. It's just the charge density wasn't uniform. So we'd get something like that. All right. Oh man, this one sucks. I just have to get that out of the way. I hate this problem. I know, I wrote it. It's just an algebraic mess. So you can probably guess what this one is, because we just did a problem about a partially inserted dielectric and it was parallel. So it makes sense that by symmetry we should include a series version. There's just a lot of computing with this. All right, suppose an insulating slab with dielectric kappa is placed partially between the plates. So it fully fills the area, but it doesn't cross the whole gap, as opposed to last time where it would fill part of the area, but it would fill the whole area, or sorry, it would fill part of the area, but the entire gap. So it's a different setup here. We're saying the capacitor holds a charge Q on each plate. So you're plus Q and you're minus Q. All right. Derive an expression for the E field in each of the following regions: air-filled and inside slab. All right, so I actually do like this part. It's only the computing I don't like. So what is the E field? Well, we actually know what this is, because we said that E field, that E from one plate of charge, given by Gauss's law, is sigma over 2 epsilon naught in a vacuum. And this is a capacitor. Capacitors aren't one plate, capacitors are two. So between the plates of the capacitor, we argued that the E field is sigma over epsilon naught, which is Q divided by A epsilon naught. There's actually an alternate way that you could have got this result. We could have said, and this actually might be more precise, so we could actually just use the Gauss law argument. But another thing we could say is that E field, we know that delta V is ED for a uniform E field. So this means that E field is going to be delta V divided by D. We could also do some more manipulating, because we know that delta V is equal to Q over C for a capacitor. So E would be equal to Q divided by CD. And we actually know what C is for a capacitor. It's kappa epsilon naught A over D. So if we do that, times D, if we do that, we get the expected result, because the D's cancel and everybody else is on the bottom. So you get Q over A times Q over A times epsilon naught, and then we actually get a 1 over kappa to show that it would get weaker in a field, in an area with a dielectric that's not 1. So this is actually true in a vacuum, which we should note, that this is like the air part. Yeah, that's definitely, I guess that's how you spell that word. Vacuum has always been one of my spelling nemeses. All right, in the air-filled region, so we just use E is equal to E of 2 plates, which is 2 times sigma over 2 epsilon naught, which works out to sigma over epsilon naught, which is Q over A epsilon naught. What about inside the slab? So remember, if your charge isn't changing, what does a slab do? What does a dielectric do? Well, think about it as dielectric. So it is attempting to remove the electric field. So inside the slab, we know that E slab is just 1 over kappa times E in a vacuum, or E in air, because we just take we take kappa to be 1 in air. So we just put on a factor of kappa. So all this is saying is we have a uniform E field outside the slab, and then we also have a uniform E field inside the slab. It's just weaker by a factor of kappa, because the dielectric weakens your field. What is the potential difference? Well, we know that our potential difference between the plates, delta V total, is going to be delta V in the air region plus delta V in the slab region. So what is delta V in the air region? Well, we know it's going to be, we can write this as ED in the air plus ED in the slab as our two potentials. E in the air, we said was Q over A epsilon naught. And let's find what D is. So in the air, notice that the total gap length is D, but the only part that's not air is the slab. So if I just remove the slab length, that would be D minus T. And then what is ED in the slab? Well, we said that in the slab, our field gets divided by a factor of kappa, and it only operates over a distance T. So we might clean this up a bit. Everybody has a Q. Everybody has an A epsilon naught. And then we can write this as D minus T plus T divided by kappa. And I might write this even again as Q over A epsilon naught times D minus T times the quantity 1 minus 1 over kappa. So we can see why I said this problem becomes quite the algebra exercise. This is just the potential difference. All right, derive an expression for the capacitance of the system. So what is capacitance? Well, the definition of capacitance says C is Q over delta V. We found Q is Q, and then we spent all this work to get delta V. We could simplify, which I would suggest doing because we know it better not depend on Q. So we get A epsilon naught over D minus T times the quantity 1 minus 1 over kappa. And now I think is now the time we jokingly say as expected, as if we somehow would have guessed this is the results before doing the problem. So this is quite a lot, and we're not done. So this gets us the capacitance of this setup. Now we're gonna plug in some values at the very end to like make sure that this works, like makes sense. It works with a 0 thickness slab or a slab of thickness D. Like make sure that that works. But first, we're gonna show that this is actually a series capacitance setup. All right, this is why I apologized in advance. We are going to show that we get this number or expression also by modeling this as capacitors in series. So if we were to model this in series, we would just do this, where I have dielectric slab of thickness T, and then I have an air gap capacitor that fills the remaining distance, so the total distance D minus the thickness T. And this isn't bad. Like, it's pretty straightforward to model, and it's also not hard to see that the equivalent capacitance is just going to be given by the series rule. And this is where it becomes a problem. Is equivalent capacitance. So I do 1 divided by my dielectric slab is kappa epsilon naught A over T, is that capacitance. And then my air capacitor capacitance is epsilon naught A over D minus T. And now we'll start to simplify some things. So notice we have some double denominators or compound fractions. So if you have 2 denominators, you can always move the second denominator up as a numerator. So we can write this as T divided by kappa epsilon naught A plus D minus T over epsilon naught A to the minus 1. Notice everybody has a 1 over epsilon naught A in common. And that's going to get reciprocated because of the minus 1. So I can factor out an epsilon naught times A. And I get T divided by kappa plus D minus T. I guess just D minus T. And that's still raised to the minus 1. And now we can factor out a T from some of these terms. So we can write this as D minus T times the quantity 1 minus 1 over kappa to the minus 1. And minus 1 exponent, of course, that means reciprocate. So I can swing that whole thing to a denominator. So we get epsilon naught A over this entire quantity, D minus T times the quantity 1 minus 1 over kappa. And that is the result. I swear, every time I do this problem, it surprises even me that it works. So shoutouts to me for getting this right with actually doing the algebra. So we see that's our expression, and does it match? Absolutely, right? It does match. And I say shoutouts to me, but I totally messed it up the first time and had to reshoot that part. You'll notice the cut between parts C and D for when I did this wrong. Okay, so now we're just going to verify a couple special cases. So by special cases, we get a nice expression if this distance T of the slab is either 0. So if T is equal to 0, we have no slab. So we have an air-filled capacitor. But if T is equal to D, we have the thickest slab possible. So we have a kappa-filled capacitor. So we should actually know what those results are. So let's check it out. So if we have T equals 0, this is an air gap. So let's check. C is equal to epsilon naught A over D minus 0. Is T 0? So we just wipe out that entire other term. And what do you know? We get epsilon naught A over D. Air gap capacitor, right? It's epsilon naught A over D. There's no kappa involved because it's all air. So we should guess what we're going to get if T is equal to D, which is, this is a full slab. So the slab fills the entire area. So C in this case would be epsilon naught A over D minus D times 1 minus 1 over kappa. We're probably looking at this and thinking there's no way this works out. But we need to trust the process here. All right, distributing the D, we get minus D, and then minus minus makes plus, so plus D over kappa. So notice the D's cancel. So I get epsilon naught A over D over kappa. So we get another compound fraction or a double denominator, which means that we can write this as kappa epsilon naught A over D. So notice our expressions. This is air-filled, and this is dielectric with constant kappa. And now is finally time we can say as expected, because I think we actually did expect that we get some nice simple cases with those. Wow, that was a lot. This is a good problem. Like, it's just a bit number crunching for my liking. I do really like it conceptually, that we could show this using the delta V approach definition of capacitance, or we could have done this with series and done a lot more algebra to get the same answer. But what I really like about it is the special cases, where we see it works out. We get order from the chaos. All right, so that's capacitance networks.